Showtime. Hey everybody. Today I'll be talking about an intro to PyTorch and a deep learning refresher. But to start, could I get a show of hands? Who all feels like they have a solid foundational understanding of how neural networks work? Pretty good, pretty good. Okay, cool. Well, hopefully this will lay a nice little foundation off of which you can build. So, yeah, today I'll go over a deep learning refresher and then some of the basics of PyTorch, such as tensors, GPUs, and go through a simple example of how you can train a PyTorch model. Now, on the website, there is a Colab notebook that you can choose to follow along with during the second half of the talk, or that'll be there for your reference going forward should you choose to use PyTorch in the future. Oh, yeah, and Nick has mentioned 3 blue, 1 brown. I think that this Deep Learning Explained series was really good for me for visualizing how neural network training works. And then also for learning PyTorch, there's this really great resource on GitHub that has 10 Jupyter notebooks you can follow along with, and there's a lot of sort of background for each of the sort of exercises that it leads you through. So, deep learning refresher. I've got a friend who, quotes his professor and says that neural networks are simply universal function approximators, which I think is really nice. But in brief, a neural network is a differentiable function that maps one type of variable to another variable. So these variables could be, images, and if the task is classification, your next variable might be a vector with probabilities that the image contained certain animals, or in a regression model, you may take in certain values representing features of a house, and the output variable is the predicted price of that house. And when training a neural network, I like to think, apologies for this, just absolute word vomit on here, but I like to think of the example of finding a line of best fit when thinking about how a neural network is trained. So if you have all this observed data, independent and dependent variables, you can find a linear function that describes the relationship between these two variables, y equals mx plus b. And this is actually not how you find a line of best fit, because this can be solved exactly. But one way that you could theoretically find m and b is to initialize m and b randomly, and then calculate the loss of the current function of the line. Here it would probably be the mean squared error between the observed y values and the predicted y values, given your function that's predicting these y's. And then you can calculate the derivative, or the gradient, of the mean squared error with respect to the parameters m and b, after which you can nudge the values of m and b in the directions of their derivatives that minimizes the mean squared error or loss. And you can repeat this process iteratively until you converge on values of m and b that minimize your loss. And this is essentially how all neural networks are trained. So each connection between neurons is described by a linear function, and the gradient of the loss, in our example before mean squared error, is calculated with respect to each of the slopes of the equations describing the connections between neurons, and each intercept. We often refer to these as weights and biases in the model. And these trainable parameters are iteratively adjusted as to decrease the loss. So this is a clip from 3 blue, 1 brown, and I think it really nicely illustrates sort of what that looks like. And this, I guess, is showing backpropagation, which is simply the process of calculating the gradient of the loss with respect to each trainable parameter or weight and bias in the model, and updating the parameters in the direction that decreases the loss. So one major advantage of neural networks is that they can model nonlinear relationships between input and output variables. And one example of where a nonlinear function better models some data is for binary classification. So predicting a 1 or a 0, for example. If this is what your ground truth data looks like with these red X's, then the sigmoid function better models the data than does a straight line. And in a binary classification model, the outputs from the neural network may be summed here, or really transformed into a scalar value, and then input into a sigmoid activation function before you get your ultimate output value. And another major advancement, I don't really remember when exactly this happened, call it 40 years ago maybe, people started using this rectified linear unit activation function in the models, which both allows these neural networks to model nonlinear relationships because this function is nonlinear, but also solved what was called the vanishing gradient problem of the sigmoid activation function, which people were using previously to model nonlinear relationships. And that simply means when you have too high in X or too low in X value, the gradient becomes vanishingly small, and that became hard to manage computationally. So people use ReLU functions a lot. Another key element of deep learning is hyperparameters, and these are not trainable parameters like slopes or weights and biases, but rather they are pertaining to the configuration of a model. So this includes things like the learning rate, which is the magnitude by which you adjust the network's parameters as you're updating and nudging things in the direction of their gradient on this loss landscape. The learning rate schedule, so you may choose to change the learning rate over time as you're training a model. Perhaps you want to take bigger steps in the beginning, and then once you find some minimum, you may decrease your step size to find the absolute, or something closer to the absolute minimum in whatever well. Your loss function, so that's what's used to calculate the error for each example. So I've talked about mean squared error. Binary cross entropy is for binary classification. We've talked also about frame-aligned point error and AlphaFold. Now the batch size is just the number of training examples over which the loss is averaged before updating the network's parameters. And the model architecture, so that's the number of layers you have in your neural network, the sizes of each layer, and also where and how information is passed. So in all these AlphaFold models, we've seen clever ways where information may be injected at multiple points or processed separately in different tracks before being combined. Okay, well, that was all the deep learning stuff. Now on to PyTorch. PyTorch is just an open source machine and deep learning framework, and it's convenient because it helps take care of GPU acceleration behind the scenes, and also tracking gradients, which I'll talk a little bit more about with some function called torch.autograd, which, I'll say more about it later. And this is currently the most used deep learning framework in papers with code, and a lot of the big tech companies, I'm sure, like Meta and whoever else, are all using this primarily. Yeah.
Do we have to have access to a GPU to use PyTorch?
There are CPU versions of PyTorch, but I think the major advantage comes with accelerated calculations on GPUs. So I think it's I've only ever used it with GPUs, but yeah, there are CPU versions. Yeah.
So building on that, are there reasonable solutions for using like OpenCL or something, just to expand the?
Yeah.
Because like obviously using CUDA is very restrictive when it comes to hardware. You need a very particular modern reactor.
Yeah. OpenCL, I don't know what that is, but I guess
Any other like backend for AMD GPUs
Oh.
or older NVIDIA GPUs?
Okay. Yeah, I mean, I've used PyTorch on my Mac with like the MPS, so I'm sure they can support multiple types of GPU softwares, but personally, I've only ever used it with CUDA and Mac MPS, but they probably have compatibility
And how
elsewhere.
was so MPS is for metal?
Yeah.
Okay, and how was it performing?
Yeah, it was pretty good. I don't know. I've got an M1, and I thought it was reasonable. Though, I haven't tried to, train some 90 million parameter model or anything with it. I just sort of mostly played around on the Mac at least. But yeah, they, if they can handle MPS and CUDA, then whatever OpenCL is, I wouldn't be surprised if they have certain compatibility with it.
So I have a Mac. What did MPS?
What is it? Yeah, my understanding is it's just Mac's sort of, I guess way of communicating between whatever, GPU accelerated code and the actual GPU on the Mac, is, so it's, some language, I guess, translating between, in our case, PyTorch and instructions for the Mac GPU, which is different than NVIDIA GPUs. Yeah.
So it natively support NVIDIA GPUs?
PyTorch? Yeah. I mean, when you download PyTorch, you'll have to specify a specific CUDA version, which will have to be, compatible with whichever, NVIDIA GPU you have and how it's set up. Okay. And when working with, PyTorch or, really any sort of deep learning library, you hear about tensors a lot, and tensors are simply the fundamental building blocks of machine learning, and they represent data numerically. Tensors are sort of, just a generalization of vectors, and they can have any number of dimensions and shapes within each dimension. And so one thing that you need to take care of is moving data onto and off of GPUs. So GPUs are constructed so that they're really fast at performing matrix multiplications, but they don't have a lot of memory on the device, and so the kind of best way to manage that is to move data from your CPU onto the GPU, then run whatever calculations on the GPU, and then move your processed data back off of the GPU and onto the CPU, so that it so that you can say plot it. So in this example, you can sort of define your device, which you can use this torch CUDA is available to check if you have, a CUDA GPU available, and if you do, you can do tensor.toDevice, which moves your tensor onto the GPU. Whereas when you first define your tensor, it's by default on the CPU. And you know, deep learning or neural networks are pseudo-random in that you know, their parameters are initialized randomly from the start, and so in order to perform reproducible experiments, it's often important to set a random seed. So you can do that in PyTorch with torch dot manual seed. Yeah. Right. Okay. Now another important aspect of training machine learning models is determining your train and test split. And so, you know, people normally aim for about 80% of your data in the training set, 10 in the validation, and 10 in test. But when performing any sort of you know, domain split, so whether that's a sequence-based split on sequence homology or identity, or a structure-based split, you know, you want the test set to be, you know, say structurally dissimilar or have dissimilar sequences to the examples in the training and validation sets. And that's because you want the validation set to you know, be sort of from within the same distribution as your training data, and that will be a measure of whether the model is overfitting to the training examples, you know, such that it doesn't model examples that are from within the same distribution because it's so drastically overfit to the training. But then the test set would ideally be a measure of how well your trained model generalizes to examples that were not in the training distribution. Okay, so in this collab notebook on the website, we go through this example, and you know, this slide might not be necessary to include, but pretty much scikit-learn has certain functions that you can use to easily generate you know, certain types of data sets. And you know, one such data set for binary classification is these concentric circles, and this is the type of data that, you know, obviously, you know, a linear sort of decision boundary would not accurately model, and so it becomes important to use nonlinear functions in your neural network to accurately classify these two colored points. And so in the example again, you know, we simply have 3 hidden layers. Now you can, you know, optionally put your, so the outputs from your model are called logits, and you can transform those logits into probabilities by passing them, if it's binary classification, through a sigmoid function. Or in the case of multi-class classification, let's say there are a bunch of different possible animals, you can use a function called softmax that will convert the raw logits, the raw values out of the model for each category, into a probability distribution. And then you will calculate the loss on those probabilities. So yeah, the kind of key components of building a model in PyTorch include you know, defining your model class, which will inherit the torch NN module. And you know, you can define your network architecture. I think using nn.sequential is kind of the nicest way for chaining layers together, but it's not absolutely necessary. But as you can see in the example, it's pretty convenient for well, defining your forward function. Yeah, so you know, ultimately the input features of your first layer should match the number of features in each training example, and the number of output features in your last layer should match the number of independent variable or dependent variables you're trying to predict. And then the in and out features of each layer should match, well, the in features of one layer should match the out features of the previous, and the out features of this layer should match the in features of the next. And then finally, you need a forward function, which tells the model how to pass a training example through its layers. So yeah, this is what that looks like. You can define your self.layerStack, which is just sequential, which takes in as many modules as you choose. So here we're going linear layer to rectified linear unit activation function, and so forth. You'll notice the in features match the number of data features in our circles data set. So there are 2 values for each example, and then we're predicting the color of the circle with our last layer outputting 1 value. And you can just call self.layerStack of x in your forward function, which then will pass your 2 input features corresponding to your x example through all these layers, and each of these layers is just a fully connected set of all those linear functions that I was mentioning before. And maybe I'll mention also that you could simply, instead of this nn sequential, just say self.layer1 equals nn.linear, etc. Self.layer3 is nn.linear, etc. In which case, in this forward function, you could just call like self.layer 5 of self.layer 4 of self.layer 3, etc. And that's essentially what nn sequential is doing. Hopefully that made sense. And then, loss functions, they just calculate the error between a model's predictions and target values, and the torch NN module has a lot of them. And for this simple classifier, where there are only 2 possible outputs, we used binary cross entropy loss, which essentially increases exponentially as the predicted y value differs more from the ground truth y value. So yeah, it's pretty much a low value when the prediction is close to the ground truth, and a high value when the 2 differ. Also important in training a neural network are optimizers, and they are simply algorithms used to update the model parameters, which may have different update rules or learning rates. One advancement is in using momentum, which effectively helps the optimizer continue to move in the same direction that it was previously, even if the current or the local gradient is small. And common optimizers include stochastic gradient descent, where you're sort of mini batching the data and descending the gradient of that mini batch. The Atom optimizer is maybe now the most popular. It uses both momentum and adaptive learning rates, and that's defined in this next one, RMS prop, which Atom is sort of a derivative of, which uses adaptive learning rates, and that just means that parameters that receive many updates are updated with a lower learning rate, while those that receive few updates receive a larger learning rate. Yeah.
How recent is the momentum one? It seems like it could be useful for getting out of like local minimum.
Totally. Yeah, admittedly, I don't really know the history, but it's certainly, the field as a whole isn't even that old, so it can't be that old. But I don't know. It's still in use. And yeah, I think the Atom optimizer is kind of the one I see most now. And it probably, knowing the field, unlike I do, it probably is on the order of like 5 years ago, I would guess. 5 to 10. What do you think? Older than that? Yeah, well, forget what I say. Well, yeah, I think that's still a popular one. Now, fitting a model, this includes setting some like context variables in PyTorch. So you'll set the model to training mode, which means that torch.autograd will be constructing its computational graph that I'll talk about maybe next, and you'll be tracking gradients, expending computational power to track gradients. You can do your forward pass with the model just by simply passing some training example or examples into your model to output your prediction. You calculate your loss. You reset the gradients stored in the optimizer before then calculating the gradients with respect to each trainable parameter of the loss. And then you update the model parameters with the optimizer using optimizer.step. Yeah, and so a huge draw of using PyTorch is that it has this built-in differentiation engine called torch.autograd. And this, behind the scenes, is constructing a computational graph for the automated calculation of gradients. So it's effectively tracking sort of how each of these variables influence the value of whatever other variables, and is saving functions that describe effectively how you can calculate the gradient of C with respect to here A and B. And then, so then evaluating the model, you set a context variable that will tell PyTorch to no longer construct this computational graph, no longer track gradients. Model eval actually is saying to not do certain things in the model like dropout, which I haven't talked about at all, but essentially it's a way to prevent overfitting or generate diversity of predictions by removing some percentage, say 10 or 15% of the connections in a neural network. And so that's what this is doing. Then this context manager, torch inference mode, is saying don't continue constructing the computational graph. The preceding operations will not have any sort of interaction with your graph, which you use to calculate gradients. You do a forward pass and then calculate the loss in your test set. Oh, and there's this really cool website where it's like, TensorFlow Playground, where you can sort of see how a neural network learns, which is fun. And you can choose different activation functions or learning rates or different types of data, and see how changing the number of neurons in each hidden layer and their activation functions shape sort of decision boundaries by a neural network over training iterations. And then, one thing that people will commonly do is make a custom data set for PyTorch, and the crucial parts of this are, for one, inheriting the torch utils dataset class, and then overriding two functions, just the length function and getItem function. And then you ultimately want getItem to return data and label pairs. In this example from the PyTorch docs, it's just showing how, if you wanted to have a custom data set with all these, in their case, images of faces with certain landmarks annotated on it, you can override this getItem function to read like an input CSV file, apply some transformation to your images, and then return your transformed data example. And then, I think this is it. The last thing, if you want to learn a lot about PyTorch, I very highly recommend the 10 Jupyter notebooks included in that GitHub. Does anyone have any questions?
Is there any reason why PyTorch seems to have dominated, at least in this industry? Because I used TensorFlow a lot, and now currently it looks like PyTorch has completely dominated.
Yeah, I don't know if I have a great answer for that. I think it's easy to use, which always helps. I've actually never used TensorFlow, so I can't really speak to why it's better. But it does all of like the gradient tracking behind the scenes, though maybe TensorFlow does that too, which makes calculation of these gradients pretty straightforward and easy. But I don't know.
Reasons,
Yeah.
that I know of at least are that like PyTorch is a little bit more Pythonic. It looks like standard Python code a lot more than like TensorFlow does. It also dynamically creates that computation graph that Ben was talking about for the auto differentiation behind the scene as you're like going through the model. Whereas like TensorFlow, you create a session and then you compile the model to create this static computational graph, which makes the model faster, but is less flexible. Although they have with TensorFlow 2.0, they have introduced the dynamic graph creation, so that's maybe less of an argument now. But yeah, it's I think mainly just simpler and easier to get started with.
One of the other reasons that I know of is that TensorFlow was the first language that came across, but then PyTorch grew in its functionality a lot quicker, so people started jumping ship. And now because everyone uses PyTorch, even though TensorFlow's kind of like increased the speed of getting its functionality out, everyone's used to PyTorch now.
Okay. Yeah.
Can you give us some practical examples of where PyTorch is used in the deep learning protein modeling?
Yeah. Well, like protein MPNN, for example, I know is written in that. OpenFold is a PyTorch version of AlphaFold. So I guess, having an understanding of PyTorch, I'm sure RF diffusion is, I haven't really looked. So maybe every one of these tools except, original AlphaFold is written in JAX because they're Google, and probably AlphaFold 3 as well, I would imagine. But I think just about every other tool that we talk about this week is probably written in PyTorch. And having a good understanding of PyTorch will enable you to go in and manipulate those models if you choose, or fine tune or do whatever. So I think.
Is there like a case for JAX currently also?
Yeah, the advantage with JAX is something called just-in-time compilation, which I guess makes it faster for some reason that I'm not totally clear on. Maybe someone else knows, but I think the advantage with JAX is that it's faster.
And it can operate on TPUs if you have TPUs.
Okay.
I think it's
Who has that besides Google?
and it'll work on their software as well.
Yeah, it's really fast. It has a very steep learning curve compared to like PyTorch, which makes it more difficult to learn. But like the just-in-time compilation is also a feature in PyTorch 2.0 now. Like the torch.compile, you can compile your model and like make it faster too. But so like they're all really converging to similar ideas. So it's kind of just a personal preference. Although most people do tend to use PyTorch now.
You talk about evaluating on the test set. Is that like process pretty much the same for evaluating on the validation set, or is it like?
Yeah, it is. That's a good question. I guess I didn't talk about this really at all, but a common way to assess whether your model has converged is to monitor the validation loss, which again is sampled from within the same distribution as your training data. And there's something called early stopping, which employs a parameter named patience, which say your patience value is set to 10. That means when your validation loss is not decreased in 10 validation epochs, then your model is decided to be converged, at which point you'll take the model checkpoint with the lowest validation loss, and that will be your fully trained model. And then once your model has converged and you have your best model with its lowest validation loss, that's when you'll evaluate that model on the test set. So the validation loss, Nick kind of alluded to this yesterday, is used in a way to assess when the model is finished training, or it is influencing training in that its loss value is used to determine when the model has converged. And then you evaluate it on the test set once you are done training. But yeah, I guess practically it is the same where you're not tracking the gradients. You set whatever context manager, like inference mode, and yeah, you're just calculating the validation loss without backpropagating any of the gradients from that loss in the same way that you would the test set. Yeah.
So when you get a model in training mode, can you expand on what is zero gradients?
Yeah, my understanding is that the optimizer is storing, the gradients associated with each trainable parameter. But before you want to let's see if I can quickly get to that. Yeah. So yeah, the optimizer is sort of storing the gradients associated with each trainable parameter, but I guess you want to sort of reset those from whatever the previous update was before you, calculate the gradients with respect to this next training step, and then I guess adjust the parameters using the optimizer.